Yeah, so I'm Barry, and today I'm going to be talking about strategic behavior in traditional forecasting competitions. This is based on joint work with Ra Frangillo, Melody Sue, and Anish Thiligar. And feel free to interrupt with any clarifying questions, but maybe save more technical ones for the end. Okay, so we're going to start off by defining what a forecasting competition is. So in a nutshell, in a forecasting competition, we have a set of competitors. So we have our end competitors, sorry, this guy, over here. And each competitor is submitting a prediction about some future event or outcome. And so we have a set of outcomes. In this simple example we have here, we're asking each of our forecasters to predict the probability that it's going to rain for several days of the week. And so we're going to say the outcome for rain is 1 and the outcome that it doesn't rain is 0. So all of these prediction vectors are passed into some mechanism, and eventually the outcomes are realized, right? So the week passes and it rains on Monday and Thursday in this example, and it ends up being sunny on Tuesday and Wednesday. And so that vector of outcome realizations is also passed into the mechanism. And given the input of these predictions and outcome realizations, the mechanism gives us some winner. So it determines who is the best forecaster in some sense. And some examples in practice are Kaggle, which is a machine learning competition, as well as the Good Judgment Project, where we have forecasters predicting on several geopolitical events. So the question to ask is, what mechanism should we use to determine who wins this competition? And the answer in practice, most competitions end up using simple max, including Kaggle. So in simple max, what we do for each outcome, we score a person's prediction or report with that outcome using a proper scoring rule. And I won't get into the details of proper scoring rules, but the idea there is that your expected score is maximized by reporting truthfully, right? Which is good because we want to measure these forecasters based on their true beliefs. So we sum over these proper scores for each outcome and prediction, and then we simply choose the forecaster who achieves the maximum. And that is why we call it simple max. It's a very simple and sort of intuitive mechanism in the community. So unfortunately, in previous literature, it's been noted that simple max has misaligned incentives, even in this really simple example. So up here, we have just 3 forecasters and we have 1 event. And let's say that that event is whether or not it's going to rain tomorrow. And let's say that the ground truth is that the probability it's going to rain is 50%. So we have these 3 forecasters submitting 3 different reports for their predictions of the probability of rain. And we have 2 different worlds that could happen. So in the first one, it ends up being sunny the next day. And in this case, the person on the left actually wins the competition, right? So again, we're encoding sunny as the outcome 0, and a proper score is going to choose the person who predicted 5%. And then in the other worlds, it rains, right? And in that case, actually the person on the right is going to be declared the winner. Again, they're predicting 95% under the proper scoring rule. And so you can kind of see what the issue is here, right? Because in fact, the person who is really the best forecaster and actually knows the ground truth is the forecaster in the middle. They're predicting 50%. But in this example, just with 1 event, they're always surrounded by the other 2, and they're never actually going to win the competition. And so they're really incentivized here to extremize their report either towards 0 or 1 in order to get that edge over the other forecasters. So this is a problem, right? And it's been noted in previous literature. And there also have been other mechanisms which have been proposed to incentivize people to behave better. But simple max is still ubiquitous in practice. Kaggle is still using it. Several competitions are. And so our question is, why are they still using this framework? And one reason that we've discovered is that there really is a folklore in the community that this mechanism should be truthful in practice, meaning if there are enough events, right? So as the number of events gets large, there's a quote we see here that people really think in the long run, it's just best to be honest. But is it actually? Nobody has really checked this theoretically. And in fact, no one studied simple max in this formal model for even more than one event. So this is kind of our main motivation for our research. We really want to ask the question, is this folklore always true? What is the incentive structure of simple max? And will people behave truthfully in the long run as we increase the number of events? All right, so we're just gonna get into the nitty-gritty of the model really quick. So this kind of lines up with the example that I had in the beginning. But we have m independent binary events, and each event has some bias, theta sub t, which is the expected value of those random events. And we're going to consider n equals 2 forecasters for the next couple of slides. Each forecaster has some belief vector, p sub I, as we saw in the beginning. So that's in the set 0, 1 to the m. And each forecaster also submits some report vector, which is also in the same space. But again, the issue is the report vector may be different than the belief in their strategic behavior. And finally, the outcomes are sampled from our random variables, and the winner is determined by the simple max. So here I've just written what I said in words before. We simply take the sum of a proper score over each report and outcome and choose the forecaster who achieves the max. And just 2 small notes, in our research, we consider the quadratic scoring rule, and that's very standard in this literature. And also, if this argmax set has more than one forecaster, then we just pick someone from that set with equal probability. Yeah.
Do the forecasters know the full vector of beliefs in advance
Of the other forecasters?
of their own, like of the events? Like, do I know my full? If I'm a forecaster, do I know the full vector of event probabilities?
Right. So we're going to talk about the actual belief distribution in a minute. So,
Great.
yeah.
Thanks.
So here it is. Yeah, so the last thing in the model is in our setting, we're considering that the forecasters have a joint belief distribution over both the outcome vector and everyone else's reports. And this also has been used in previous literature, and this allows for a pretty general understanding of uncertainty. And for example, a Bayesian setting maybe where people have different pieces of information that they receive and then they update about the outcomes and what other people believe and report. So it seems like uncertainty should maybe smooth out incentives. And that's kind of the intuition we had coming into this, because it should be hard to strategize if you don't really know what's going to happen or what other people are going to say, right? So do we see truthful behavior for a large number of events M? And so our intuition for our result is, surprise, we don't always see this truthful behavior. And so in this example that we have 2 forecasters, I and J, and they have their score distributions plotted up here. So this is just the PDF of their scores over 100 events. And we can see there's a big separation between their distributions, right? So the blue forecaster is pretty far behind and the red is far ahead. And so the intuition here is that the forecaster who's behind, forecaster J, is going to attempt to increase the variance of their distribution, even at the cost of lowering their mean, by extremizing their reports. And the reason they do this is they're able to basically increase that overlap area that they have with the other distribution and increase their chance of getting lucky and winning. And then meanwhile, the good forecaster who's ahead is going to actually decrease their variance at the cost of lowering their mean score. And again, you can see that this decreases the overlap between these 2 distributions. And the way that they do this is they basically hedge their reports towards the other forecaster. So they're going to actually hedge. And so we have a simple example here to illustrate that hedging behavior. So say we have M events, and forecaster I, the good forecaster's belief, is equal to the ground truth, and that's 0.9 for every event. And meanwhile, forecaster J has belief 0.5 for all the events, and they're reporting approximately truthfully. So they're within 0.1 of their belief. So they're in this, interval here. And so the worst case of forecaster J, in terms of their score, ends up being 0.84 M. You can just see that in the fact that, let's say that their report direction aligns with the outcome, right? So they report 0.6 if 1 occurs and 0.4 if 0 occurs, and we just take the sum of scores in that case. But what is the set of outcomes where I will definitely win by reporting truthfully? So in fact, what happens is if we have K ones, right, then they end up with a score of 1 minus 0.1 squared by the proper scoring rule being the quadratic score. And if 0 occurs, then they receive 1 minus 0.9 squared. And in fact, if you do a little math here, I is guaranteed to win when at least 82% of those event outcomes end up being 1, right? But let's say that instead, I decides to report 0.8 for every event, right? So what they're doing is they're actually hedging their report slightly towards the middle where the bad forecaster is. And in that case, I is actually guaranteed to win when at least 80% of the event outcomes are 1. And so this is a strictly bigger set of outcomes where I knows that she's going to win over J. And what's also kind of happening here is actually, again, the mean aggregate score that I gets decreases slightly, right? Because they're losing something from under their belief by moving from 0.9 to 0.8, given that they think actually 90% of the events are going to be 1. But the variance of the aggregate score also decreases by making this hedging move. But luckily, there are still conditions that we've discovered in this two forecaster setting where incentives are aligned. So at a high level, the idea is we have our two forecasters, but their distributions are much closer, right? They're overlapping much more. And so there's a lot more uncertainty about who's going to win. And both of them think they really have a shot at winning this tournament. And so we're going to have this informal condition. Feel free to ask me about the technical details later if you'd like. But we're going to assume from forecaster I's perspective that 1, her belief distribution about J's reports is smooth in some way in terms of continuity. And then 2, the probability of winning under any best response from I is around 1/2, give or take, right? And so that second condition is basically saying that forecaster I has a shot, like I said before in our intuition slide. So she thinks that there's a probability of winning, but you know, she can't be too far ahead nor too far behind from her own perspective. And finally, the last sort of technical piece, let sigma I squared be the minimum variance of score differences according to I's belief. We take the variance of the sum of score differences between our JT, which is the other forecaster, and then their report RIT. Again, this is over the joint belief distribution model that we mentioned before over the other forecasters' beliefs and the outcomes. And we just take the minimum over any report vector that I could submit. So given the previous condition and the last slide holds, we've shown that forecaster I is going to be gamma approximately truthful, where gamma is in big O of sigma I to the -1/2. So 2 things. The first, what does approximately truthful actually mean? We're just saying that the L infinity distance between the belief and report vector is going to be less than gamma. So just the maximum difference between any report and any belief is bounded above by that gamma. And so really what we're seeing here is that the approximate truthfulness parameter, the distance between this report and the belief, is going to decrease as uncertainty grows, right? As this variance term grows. And obviously, as we add more events, that variance is only going to increase. But remember from our previous condition that we must have the score difference to remain close to 0, right? In the sense that your probability of winning is never going to be too high or too low. And so we don't expect, you know, with a large number of events, the disparities between forecasters is only going to increase. So eventually we're going to sort of leave this regime where we have this result. So just a quick aside with a one slide intro, we also worked a bit on a very different version of this game with some interesting results that we'll call the full information game. So in this setting, everyone knows the true probabilities and others report. But even with that very strong assumption, there's some really cool results that we're working on in terms of characterizing what's happening in Nash equilibria. Just as a note, this is actually a discrete version of the hoteling co-location game, if anyone's heard of that, where firms choose some location on the 0-1 interval and customers visit the closest firm. But yeah, we have a couple of results that we'll advertise here. One is that the average distance between the report and ground truth actually decreases in the number of events. The other is that for few enough events, first, pure Nash equilibria do exist, but in those equilibria, agents are always extremizing, as in their reports are always either 0 or 1. Okay, so just some closing thoughts. So surprisingly, our results show that non-truthful behavior occurs for both small m, or small number of events, and large number of events. But simple max can still have good incentives under some reasonable conditions. And what's really key for that is uncertainty. And so one thing that, competition should factor into account is that they really need to avoid leaking information about other people's scores, because we want to make sure people kind of are uncertain about where they're at and how they stack up against others. The second, as I said before, is that competitors need to really think they have a shot in order to use the guarantees that we provide for approximate truthfulness. And so we hope that forecasting competition platforms can use these results that we've described to really inform how they decide to run their mechanisms and their competitions to ensure that people are behaving the way they want them to. Okay, that's it.
Yeah, we have time for a few questions.
Yeah.
Have you thought about it all, or do you think it might be impossible, for with this structure where one guy gets the whole prize money to do something that is truthful?
Yeah, so as I mentioned before, there are multiple mechanisms that other people have actually written papers about, including Anish. And so there are mechanisms which guarantee sort of approximate truthfulness. And they've been out for a couple of years. I think part of the motivation for this paper was that people haven't really been adopting them for multiple reasons. Some of them are random and people don't really like that. So we really wanted to delve into what's going on with the simple max, since it's still really used in practice.